So this assumption, okay, in this assumption, we normally will say the variables are independently and identically distributed, or abbreviated as IID. Okay, they are IID variables. Okay, so this is like a technical term, okay, used in statistics very often. Okay, of course, this is not always the case. Okay, here, I mean, we have a non-IID variable. Okay, for example, okay, let's consider, okay, we try to sample the temperature, okay, from the atmosphere. Okay, oh, sorry. Yeah, the atmospheric CO2 measurements, okay, because we know like CO2, okay, if you look at CO2 distribution just for a short period of time, of course you can assume it doesn't, it is IID. But if you see that we are considering this experiment from 1959 to 1997, so obviously, okay, the CO2 distribution is not identical, right? Because we know, okay, the CO2 gets accumulated over time. That is why we have this 温室效应. I don't know the English term, the something house, right? But I forgot. Greenhouse effect, if I remember. Okay, greenhouse effect. Anyway, this is like how the CO2, okay, distribution gets like changed over time. Okay, and obviously you cannot assume this, for such a long experiment period of time, the CO2 distribution is IID. That's not the case. That's obviously not the case. Okay. But again, let me remind you, this is because the experiment, the period we are considering is quite long. Okay. You see the x coordinate, okay, represent the year. Okay, actually runs from 1955 to 2000. So it's almost half a decade, So in such a long period of time, like, a lot of things can change. But if you only consider this experiment for maybe like an hour, then you could assume this IID, right? For CO2 measurement, okay? You can consider it's IID, if it's only an hour. So it depends on a lot of factors, okay? It depends on, how long you consider the experiment is, okay? And also like a certain sample, like a process, okay? But anyway, okay, in this class we assume, the variables are, IID, okay, variables, okay. So for the models that we consider, okay, models are simplified description of a given system or process, okay, that we are interested in, okay. So this description normally is mathematics, and as I said, they have certain parameters to control them. Okay, so those descriptions are deliberately designed to capture only the most relevant aspect of the system, okay, and not to explain every minor detail, okay. after all, okay, if you want to model something in mathematics, you have to simplify it, okay? If you do not simplify in the model design, then you cannot have a model, or your model will be too complicated to work with, okay? So remember, you say, how about a certain minor factors that we do not consider in the model design? That's fine. Remember, in this class, the model we are considering are probabilistic. Remember? And you can take that minor factor, okay, into account, okay, because the model is probabilistic. So those probabilistic, aspect can be considered as the impact from those minor factors. Okay, so this is one reason. A more complex model is not always better one, because it lacks explanation. It is not, easy to work with. Okay, so there are many different kinds of models, obviously. So in this class, we'll restrict ourselves to Bayesian model. Okay. So here's the Bayesian modeling process. Okay, let's go over this quickly. Okay, we actually will, as I will say, later. This is this process may be, done, multiple times. It may be done. Maybe we may need to go through this process iteratively. Okay. Given some data and some assumptions on how this data could have been generated, okay, we design a model by combining building blocks. Okay, what are those building blocks? Okay, those building blocks are probability distributions. The most well-known one is, I already told you, the Gaussian distribution or normal distribution. Okay. And there are other distributions that you are going to see. I hope to be able to talk about the beta distribution today, but let's see. Okay, so most of the time, these models are crude approximation, just approximation. Okay, but most of the time, okay, this is good enough. Okay, good enough. And then we use Bayes' theorem, okay, to add data to our models. And then we derive the logical consequences. Okay, so that's the Bayesian inference. Okay, the first one is really the model design. The second part is the Bayesian inference. Okay, so at the end, okay, we are conditioning the model on our data. So data becomes, in the Bayesian inference, eventually data will become the condition. And the model parameters will be, we'll see the distribution for model parameter based on condition of the data. Okay, that's the second one. The third one is, then we need to, check the model, okay, to see if it makes sense according to different criteria, okay, such as, the data, our expertise on the subject, okay, the understanding on the subject, if this is plausible, and sometimes by comparing several models. So this is we need to be able to explain the result, okay, of the inference and make sure it is plausible. Okay, so if it's good, great. Okay, but we may need to go over them multiple times. Why? Because later on you may collect more data, right? You may collect more data, so you may need to go through the process multiple times. And also, if this result is not plausible, it is against the intuition, okay, or against the the knowledge on this subject, then what happens is that, okay, either the model, okay, design has some problem that you didn't take into account the important factor. Okay, I'm not saying the minor factor, I'm saying the important factors. Okay, either that's the case, or something's wrong. When you put those probability distribution together, something's wrong. So anyway, you may need to redesign your model, or the data collection could go wrong, right? I mean, the data collection, may be biased, okay? But anyway, okay, so you find out the problems, okay, and then redo the whole thing again. So this is, as I said, this is more like a iterate, even though this looks like 3 steps, but we need to, a lot of time need to go through them like iteratively. And it may be nonlinear. Why is it nonlinear? Because if the model works, okay, if you just collect more data, then you start from here, okay, and do this again. But if a model has problem, of course you need to go back to fix the model, okay, fix model design, and then do it again. So it depends on the situation. So that's why I say, we say this is non-linear fashion. Okay. So Bayesian models are also known as probabilistic models, okay, because they are built using probabilities, okay. They are based, actually, the Bayesian models are based on probability distributions. So it will be, we will be talking about a lot of different distributions in this class, okay, at a later time, okay. So because probabilities are the correct mathematical tool to model uncertainty, well, we talked about that already. So let's take a walk through the garden of forking path, okay. So distribution. The probability distribution should reflect what we know about the value of it doesn't show up. The theta parameter, the theta, it's not showing up. There's a theta parameter, okay, before seeing the data, which is D, okay, capital D, okay, this is, I hate it. We are talking about this theta and the D. Okay, one dimension represents the theta for the model parameter. One dimension model the D, okay, the data, okay, D. So I'm talking about the theta and D here in this table. Okay. So if you know nothing, like Jon Snow, do you guys know Jon Snow? No? Okay, then you guys don't know the movie, the TV series. There's a TV series called what? The novel is called The Song of Ice and Fire. 冰与火之歌. When this novel becomes the TV series, it's like the Game of Thrones. Do you know this TV series? So this Jon Snow is actually one character in that story, okay? Because that guy came out of nowhere, okay? So nobody knows his background, okay? So that's why the author of the textbook use this guy's name, okay? Just want to give you an idea, okay? That I mean, this guy, because it come out of nowhere, nobody knows his background, so that just like we know nothing, okay? And by the way, I mean that TV series is very famous. I think they won like some awards, and it's a very good TV series, okay? So we could use flat pliers, just like uniform distribution, just like what I said, okay? That basically means that you do not commit to a certain value. During this, the only thing you know is, okay, this theta, okay, has a certain, valid range. Maybe it is good, okay? It could be in between 0 and 1, so you just use a flat plier there, or it could be good from 0 to maybe 100, okay? Then again, in between these two extremes, you use a flat plier, okay? So that's a very simple approach, okay? Use flat plier, and then okay, use the Bayesian inference, and it will give you the more plausible result, okay? So in general, we can do better than pliers, than the flat pliers, because sometimes we know something, know something better. For example, remember like the flip coin. Okay, if the flip coin comes from the government, you may say